Okay, hope you enjoyed the video on the gravity and how we actually understand what's the meaning of a gravitational field as well as a gravitational field strength. So just to recap on that video, basically, okay, over here we are at page 71. If you look at gravitational field, it's a region where mass experiences a force due to gravitational attraction. So now we know that that force actually depends on two things. It depends on the size of the objects as well as the distance between the two objects. Okay, so next we're going to talk about mass and weight and their relationship. So what's the difference between mass and weight? We're going to explore over here in this second video. We learned in chapter 3 this formula, universal formula, resultant force equals mass times acceleration. Okay, we can actually use this same formula over here. Do highlight this. This is the first formula of two that we need to learn in this chapter. That is W equals mg. That's not exactly a new formula. As you can see here, W is basically the mass, the force, whereas m is the same as the mass and g is the gravitational acceleration over here. So over here, we instead of gravitational acceleration, we actually use gravitational field strength. So to highlight this, this formula is actually from F equals ma. So acceleration of free fall is equal to 10 meters per second square, and this is actually equal in value to the gravitational field strength. To put a star here, we actually use this number interchangeably. Okay. So over here, same thing for the formula W equals mg. W is the weight in newtons, m is the mass of the object in kilograms, g is the gravitational field strength, which is what we learned in the previous video, and this unit is newtons per kilogram. Okay, we are at page 72, at the end of page 72, looking at an example here, just a very simple example. If they give a mass of 75 grams, find its weight if g is 10 newtons per kilogram. So first thing to do, as you can see from this formula, okay, the mass of the object is always measured. All these units are in SI units, so it's in kilograms. So now we can see yet another example of how important SI units are. Okay, it's mainly used in the application of formulas. Okay, so a mobile phone of 75 grams, first thing we need to do is to convert it to kilograms. So just highlight this, write this down, must convert to kilograms first. And after that, you can just use the formula W equals mg to find its weight. Okay, in this part of the book, I'll just let you cancel this thing off. Because some weighing instruments like spring balance and bathroom scale actually measure weight of an instrument. Electronic balance, actually, we measure the mass. So I think this is a mistake over here. So the electronic balance over here used to measure mass. Highlight this part. Okay, you can see an elephant here. Okay, on the earth, on the moon. Obviously, if it's on the moon, it will die, right? Because there's no air. So if it is on earth, what happens? Okay, you can see the mass here is this same mass. You notice, both the mass are the same and the weight is different. Okay, so if you to weigh an elephant on earth and moon, the weight will be different, but the mass is the same because same amount of atoms and molecules. It didn't lose weight, right? So how is mass measured? Okay, to avoid to calibrate weighing scales on different gravitational field strength, we actually measure mass using beam balance. Okay, just like you highlight this part here at the bottom of page 73 is a good summary of the difference between mass and weight. This is very important. Mass, as we mentioned, is the definition is the amount of wet matter, whereas weight is a gravitational force. Mass is a scalar and weight is a vector because vector has a direction and magnitude. Okay, SI unit for mass is the kilogram, whereas for weight is the newtons. Mass is independent of gravitational field strength. It means it doesn't depend where you are. You can have gravitational field, no gravitational field. You can have strong gravitational field like on Earth, or even stronger like on Jupiter, because we know Jupiter is much bigger than Earth. It's one of the biggest planets in the solar system. Okay, and weight is actually dependent on the gravitational field strength. Okay, whether you're on Earth or the Moon, your weight changes, but over here the mass don't change. Okay, and finally, Mass is measured using beam balance and electronic balance. You notice over here, one of the keywords here is balance, because as you can see here on the right of page 73, this is a balance. This is how we actually, the instrument we use to measure mass, actually using principle of moments here. So it doesn't depend on the location. You can be on the moon, you use this machine still works. It still tells you the mass, because it is already calibrated based on masses that are already known. Okay, so the weight is measured using a spring balance or bathroom scale. Okay, spring balance over here, don't really like to use this word, but it gives you the idea of balancing, so of measuring mass, but not exactly. Okay, the more important word here is spring. So since it's using a concept of a spring is able to extend or contract. The amount of contraction or expansion actually depends on the gravitational field. So just remember that spring balance, instead of just looking at the word balance, look at the word spring. If it has something to do with gravitational field, so it must measure weight instead of mass. And the other one we know is the bathroom scale. So, okay, just another simple example here. Acceleration of free fall on the moon and Earth is this. So just highlight this. Okay, they ask you to find what is the weight of the rock on Earth. Okay, if you have mass 10 kilograms, the rest is just formula. They give you M, they give you G. Weight is simply W equals mg. Okay, for both the Earth and the Moon. Just make sure we use the different G value. Okay, so does it make sense? It makes sense that weight on Moon is less than weight on Earth. Okay, yet another one over here. What happens to A, the mass and weight of a satellite as it's launched from Earth into space? Okay, what we mentioned earlier in the first video, mass will always remain the same because we don't change the number of molecules, and mass does not change at different locations, as in different planets, different gravitational fields. Okay, what about the weight? Since the weight depends on the gravitational field, okay, and is weaker in space than on Earth, the weight of the satellite decreases as it moves from Earth to space. Alright, so just a recap here on the first two videos. Mass is the amount of matter, measured in kilograms, whereas weight is a force, measured in newtons. Okay, weight, the formula is W equals mg, and we talked about gravitational field strength. It's basically the force per unit mass. And it's basically the same value as the acceleration of free fall in the same place, and that's important. So the weight actually of an object varies depending on the strength of the gravitational field, and the mass is a property that does not change. Okay. So even though there are changes in the gravitational field strength. Alright, hope you enjoyed this second video. Okay, next up, I will actually be showing you another short video on the difference between mass and weight. Okay, do enjoy this. See you again soon.